Here's an example of two populations, and we're testing a hypothesis on proportions. Louis Pasteur had conducted a series of experiments that demonstrated the roles that yeast and bacteria play in the fermentation process. These results gave Joseph Lister, a British physician, the idea that human infections might have a similar organic origin. Lister developed a theory that using carbolic acid as a surgical room disinfectant would improve the postoperative survival rates for surgical patients. Out of the 40 patients amputated with the use of carbolic acid, 34 survived. Out of the 35 patients amputated without the use of carbolic acid, 19 survived. Joseph Lister was working on this in 1865. It actually took quite a long time before the medical community really understood and appreciated what Lister had done. But let's see if this idea of disinfecting surgical utensils is actually beneficial. So here's how we would use a hypothesis test for this situation. A couple of questions to get us started. What proportion of patients amputated with the use of carbolic acid survived? So amputation, they're cutting off a limb, an arm, or a leg, and then letting it heal back, right? So proportion of patients amputated with the use of carbolic acid. So with carbolic acid, we had 40 patients and 34 survived. So the proportion would be 34 out of 40. And if we pull up our handy dandy calculator, 34 divided by 40 would give us 0.85 or 85%. What proportion of patients amputated without carbolic acid survived? So looking at the next line, I had 19 survive out of 35. And we get 0.54. That's a pretty big difference. But let's see if it's statistically significant in its difference. We're going to test the claim that carbolic acid improved survival rates using a 5% significance level. We have our values for x1 and n1 and x2 and n2 that we'll use in our template. And we also have alpha is 0.05. So we'll let the first population be with carbolic acid and the second population be without. Before we set up our hypotheses, we need to check our assumptions. And the assumptions for two population proportions are that we have at least 5 successes and at least 5 failures. So n times p is greater than or equal to 5. And n times q is greater than or equal to 5. We're going to assume random samples, and we're also going to assume that the data are independent of one another. So we're keeping these two groups of people separate, and what happens for one person in one group does not affect what happens in another person in another group. And for each of the two samples, the number of successes is at least 5, and the number of failures is at least 5. If we're looking at our sample data, 34 survived in the first population, 6 died. So we have greater than 5 in both cases. And then for the second population, 19 survived and 6 died. Again, more than 5. So we can set up our hypotheses. And for this, we're talking about proportions this time. So we'll use P, P1 and P2. Null hypothesis is always equality. Recall that with carbolic acid is our first population. So P1 is referring to with carbolic acid. And our claim is that carbolic acid improves survival rates. Survival rate is our proportion, the proportion that survived. So we want this alternative hypothesis to be greater than. P1 is greater than P2. And this will be our claim. Now we can pull up our template, and we're going to leave this difference in proportion to be 0. There are some instances where we might want a difference in the proportions, and those create different types of problems that are also built into this template. We tend not to focus on those types of problems at this level, so we'll just leave that at 0. The alternative hypothesis that pi1 is greater than pi2. But this is the proportions. Proportion 1 is greater than proportion 2. We do have a level of significance, 0.05. We'll leave that there since that's the significance level for our particular proportion test that we're doing. And then first sample size N1 is 40. Number of successes for population 1 is 34. Notice it calculates our P1 value, 0.85. And then for the second population, we had 35 and 19, and it gives us a P2 value, 0.54, as we referenced earlier. And then we've got some calculations going on. So the pooling P bar is 0.7. So I'm going to show you in your notes, that's referring to this P bar formula right here, the pooled sample proportion. So looking at this estimated pi from pooling P 0.7. That's what this is referring to. And then some more values. We have our critical Z value, 1.645. That one definitely looks familiar. We've seen that one before. And we've got our Z score of different sample proportions, 2.9, and our P value of sample proportions, 0.0017. So I'm going to highlight these values in purple so that you can see them very well. The critical value 1.65, test statistic 2.91, and our p-value 0.0017. Notice we have a reject the null hypothesis, which is what we would expect. So coming back here, we could draw our graph before or after we plug in the numbers, it doesn't matter. 1.645, we had 2.91, and this is in the rejection region. So we would reject the null. If we were doing the p-value method, we would compare the p-value 0.002, 0017. We can round it to 0.002. I can compare that to my alpha, and if I go 2 places away from that decimal, I see that I have a 0 for the p-value and a 5 for the alpha. So the alpha is definitely bigger, which would lead to another rejection. The p-value is too small for that sample data to come from populations with this same proportion. So we reject the null. What does that mean? There is enough evidence to support the claim that carbolic acid improves survival rates. Additionally, referring to this example of the infections and amputations, we can also consider a confidence interval. So if we scroll down on the template, there is a confidence interval for P1 minus P2. We'll leave that 2 there, and using the alpha all the way up here from above, so our alpha is 0.05, we can get our 95% confidence interval. We see that 0.108, 0.11, and 0.51 would be our confidence interval. So a 95% confidence interval, if we want to pursue that, 0.11 to 0.51. Since both of these numbers are positive, we see that 0 is not contained in the interval, which means it is very unlikely that these two proportions are equal. So again, more evidence to support our claim that carbolic acid is improving survival rates. We don't have a 0 in this confidence interval. So to get the confidence interval on the template, we would need to enter the things in yellow. So we would need to enter our level of significance, our sample size, successes, sample size, and successes. And then if we're only doing a confidence interval, we can skip all of the hypothesis testing stuff, go all the way down to the confidence interval box, and the teal box is here showing our lower and upper limits for the confidence interval.